So I changed the title that Dima assigned to me a little bit. So I'm an experimentalist, so I cannot really talk about the theory. So I want to discuss a problem, the dark matter problem, and showing you the evidence, the mysteries, and how experimentalists are performing various searches, trying to figure out the nature of the dark matter. Just a word about where I come from. I come from Shanghai. And Shanghai Jiao Tong University is my official affiliation, and we have a particle, mostly particle and well, it's a fundamental physics institute called Tsendaoli Institute, where we are really keen on trying to understanding the fundamental nature of how the universe works. And so we have particle, we have astrophysics division, and also we have a quantum science division. And this is a place that we hope this is going to also be a global hub for physicists. So if you have a chance to visit Shanghai, just stop by. It's like 20 minutes from the Pudong Airport. Okay? Okay, so I saw in the, Telegram yesterday, someone was doing stargazing. I don't know, did you guys have luck of seeing the Milky Way? So let me start with the center of the Milky Way. Okay? Oops, wrong way. Did I get things backwards? Okay, maybe not the center of the Milky Way, but our solar system, okay? So when you, we know how far away from the sun, okay? All the planets, yes, hopefully. From distance from the Earth to the sun, it's called 1 AU, okay? So this is plotting as a function of the AU, and we are here, okay? And then what you see is the change of the velocity, assuming that, okay, let's ignore the elliptic orbit, everything's circular. And so velocity as a function of the distance to the solar system. And as you would imagine, the further you are towards the sun, the slower you are making the orbit, okay? And this comes from the Newtonian mechanics. Can you see the pointer? Yes. This is a bad color, but it goes with 1 over the radius square root. And the heavier the center, which is the mass of the sun, the faster you will rotate. But the further you are going away from it, you are rotating, oops, what did I do? Anyway, so this is really the high school physics that everybody hopefully is well known to everybody. Now, let's move away from the solar system. If I tell you that I make an observation of something, let's say close to the center of the galaxy, and then you see the stars like the sun are orbiting somewhere, close to the center of the galaxy. All right, so people have done this using the very, very high angular resolution telescope to look at the center of the galaxy. And then they are following, for example, stars very close to it and try to measure what their orbit is. And this is a picture showing their orbits, okay? They're elliptical, never mind, but and they gave these stars names, okay? Let's just take one of it, for example. It's rotating so fast that you can track its frequency, okay? How fast it's orbiting, one cycle. So you do this tracking. And now, by the way, this has been awarded the Nobel Prize 4 years ago. And let's do a Nobel Prize question, okay? And see if you can get it. To make life simple, let's assuming that all the orbits are circular. Imagine one of the stars has a speed of 5,000 kilometers per second, okay? With approximately 120 AU, okay, to the galactic center. That's the distance, 120 AU. Now, please stare at the previous graph a little bit, so save you a little bit of the calculation. Look up how fast the Earth is orbiting around the sun. Okay, you know that. Yes, that's the Earth, and the unit is kilometer per second. All right, so without memorizing what the big G is, you should be able to estimate the gravitational center that makes the star orbiting around it. And can you do an exercise this way? Yes? Please. You should spend 2 minutes and verify that you can get the Nobel Prize this way. Please.
What is it? What kind of stars is moved in last?
You mean the around the galactic center?
Which stars?
Oh, it doesn't matter. So I believe it's this one that I picked, but it doesn't matter. It doesn't matter which one it is, but I give you the speed and I give you the distance.
And you plug it in the formula.
Huh?
And you plug it in the formula written on the first.
Well, it's more complex. Plugging in the formula, you have to know what G is. I don't know. I'm too far away from high school, so I don't memorize what the G is. And then, the point is that it's much simpler to express this in the mass of the sun. You can scale with what we know about the Earth and the sun. Yes? And it's a simple scaling, and that's what I do all the time. Instead of really punching the numbers and do calculations, you do scaling, you do approximations. Yes? Who's brave enough to give me an answer? Well, if you saw the news 4 years ago, you probably saw the Nobel news. It kind of tell you, but that's a good way of checking whether you get the right solar mass.
3 times 10 to the 9.
10 to the 9 solar mass?
That's 6 or like.
What do you get? 10 to the 9 solar mass? 10 to the 6? Any other answer? 10 to the 1,000? That's so. This is really taking the ratio. Oops, going back, right? So G doesn't change. The question is, the answer is what m is. We know that the velocity is how much? It's a factor of how much bigger?
It's about 20 masses of the sun.
20 solar mass?
Yeah. Yes, 20 solar masses.
Really? That's the galactic center, any other answer? See, here is the thing,
Correct. Correction, the 6th power.
10 to the 6th power. Very good. So, good. So anyway, you see we got 3 different answers. There are probably more. That's the whole point of doing exercise online. That means that it actually keeps you thinking a little bit. This is a simple question. You know the ratio. You take the ratio of the velocity. You take the ratio of the radius. The ratio of the radius is about 100, a factor of 100, yes? And the ratio of velocity is 5,000 divided by 30, yes? And then you take these 2 factors together, and that will give you the ratio of the mass to the sun. And that's about 10 to the 6. And then if you read the news of the Nobel, it says they find something which is compact at the center of the galaxy, which is of that order, 5 million solar mass. And was identified, cannot see directly, it was a black hole or some compact object that you cannot see directly with optical method, but was discovered this way by looking at the orbits. Okay? Good. If you can do this, you can do the first little question from one of the project I gave. Let's keep going. So far, so good. Okay, so let me skip this. Okay, so aside from just looking at orbital motion by tracking the motion of a given star, you could also do something smarter, okay? Hopefully you also learned this from the general physics, that any wave that's propagating, if the carrier of this wave or the emitter of this wave has a relative velocity to the observer, you get some shift, right? Either it's blue shifting or red shifting, depending whether you're moving away or getting closer. If you're moving away, the frequency of the wave is becoming bigger or smaller? It's going to get smaller. Okay? This is true for non-relativistic wave, and this fact happened to also be true for the photon wave. Okay? So good. Now, we also have golden standard that we have fixed frequency for something that's in the rest mass. And the best frequency is atomic frequency, okay? Because that's a fixed energy, and fixed energy have fixed frequency. In fact, if you wonder whether if the quantum mechanics works at the other side of the universe, the answer is yes, because those lines were observed only with the correction of the redshift, how far away they're from, but they do work. Okay, so looking at the hydrogen lines, you can do this, okay? So hydrogen has a lot of lines, okay? You'll be amazed how much lines these atoms have. But the first discovered series of hydrogen lines is so-called the Balmer theory. What it is the transition of between the higher hydrogen orbits to its second closest orbits. Okay, so it's like n orbit all the way to jumping to its second orbit. But depending on where it comes from, it has several different colors. Okay, there is a lines that have been very much used in astronomy called H alpha, which I will show the wavelengths later. But here gives you sort of a formula of the so-called redshift. What's called redshift is like the fractional shift of the frequency, okay, relative to its original frequency. Okay, typically in astronomy, people give it a z. Okay, and z for a motion which is really away from us, v parallel. Assuming v is relatively small compared to the speed of light, it's just the ratio of them. Okay, that's very easy. Okay, so if you look at the sky, you see, look at the lines corresponding to the hydrogen alpha, and then you just measure its relative shift to its nominal value, and then you know how fast it's moving in the radial direction at least. Okay, there's a more complex shift if the thing is moving in a transversal direction. Okay, it's another correction, but let's ignore that for now. Okay, let's fast forward to about 50 years ago. Okay, so a measurement like this has been done at the galactic level, meaning that you can either look at the star closer to us, or you look far away, outside our own galaxy, and look something else, and then look at how do these stars move, okay? Although they are moving in maybe some weird orbits, maybe not really radial to us, but they also maybe have a transverse direction. But you can map it. You can measure all these stars, the hydrogen lines from all these stars, and they don't move in one direction. They could be orbiting, but such a measurement has been very carefully done by Vera Rubin and her collaborator Ken Ford. And they did systematic studies of all these stars. And you could even look up the original paper. Those are beautiful papers that you can read even with a fresh mind. You don't have to understand too much. This is one of the galaxy they chose. It's called M31. Okay? If you are very annoyed by these symbols, M31, this is the first extragalactic, at that time called nebula. Nowadays it's called galaxy. That's outside our Milky Way, discovered by Hubble in 1931 or 29. I forgot, but that was the first one that human beings actually know there was something beyond the Milky Way. Okay, so look at this, and they selected some of the stars on the disk that they could track, and just measure the hydrogen lines of them. Okay, and then, as I just told you, based on that, you can measure the the speed that it's rotating, speed component, for example, they can decompose the speed into various directions, so on and so forth. So these are very nice measurements. Okay, so just give you a sense how is this measurement done. Okay, so you see every star, they characterize a star in terms of some coordinate relative to the center of that galaxy, and then looking at all these lines. To the first glance, everything lined up. Okay, so hey, quantum mechanics works. Yes, it does work, because any of these stars are sort of tracking the same hydrogen line, except if you look extremely carefully. I'm helping you with this vertical line that I draw on the PowerPoint, okay? And if you think this page is not really tilted, and then you can look extremely carefully that some of these lines are a little bit to the left, to the right of this green line, and over here it's the other way around, okay? So you are seeing some pattern, some very interesting pattern. And what that is if you look at sort of one side of the galaxy versus the other, because they are circling, okay? Therefore, relative to the galaxy center, if you look at one side versus the other, their speed is, their velocity is opposite, okay? And which means that, relatively speaking, yes, one is red shifting, one is blue shifting, so to speak, okay? So that's the signature, okay? So you can convert that into something like radius to the center versus where the line position, okay? Very easy. And also I'm drawing a little PowerPoint line to help you to see this. This is not obvious, so you have to do very careful analysis, by the way, in order to figure out exactly how much is shifted. But that's the signature, okay? Now, if you look up the book, okay, the H alpha line is nominally at 656 nanometer, okay? But this is at the center. What you see is something like 660 psi, rather. Although it's the same digit, but it's not the same number. And on top of that, you see on one side versus the other side, you see a relative shift of that shift. Yes? All right. I have a question. Why does the observed lines, even at the center of the galaxy, is incorrect or shifted against the nominal value? Very good. I'll talk about it later on. This is called Hubble expansion. Okay? It itself is also moving, but the stars around it, it's moving. Okay? In any case, the name of the game, in order to track the speed of these stars relative to the galactic center, is just looking at the fractional frequency shift. And then you can measure the velocity distribution as a function of radius. Let's keep going. Not moving. Here's the result. Okay, you see all these in the original paper, Vera Rubin's paper. She says this is the rotational velocity as a function of distance to the center. You see on one side is this way, the other way it's negative. Okay, so makes sense. Everything seems to make sense. By the way, just to give you a scale of this speed, remember at the galactic center, we were looking at something which is 5,000 kilometers per second. And over here, it's about a factor of 10 less, okay? Hundreds of kilometers per second. And for our Earth circulating the sun, we are about tens kilometers per second, okay? So, so these are numbers to bear in mind. Okay, now the situation of the galactic motion is more complex in the sense that we cannot just assume that it's a single thing at the center, located at the center. We cannot assume that everything is just like a black hole, because all the mass are distributed, yes? And the mass distribution, if you don't ignore everything else, will be concentrated by the mass of the stars. So every star itself contributes to the gravitational potential, so you have to take all these into account. But let's still try to make our life simple by assuming that we have a we have a spherical distribution. Okay, everything is symmetric. And then things can be simplified in that the so-called Gaussian theorem, that the speed at any given radius r should go with the sphere that covers this radius, the total mass, as if this mass is just concentrated at the very center. And then it follows all the old formula that you use to derive the mass of the black hole. Okay? So the velocity, based on velocity, then you can derive what the mass distribution is. Okay? Sphere and by sphere by sphere, and then you track, you measure everything. So that was the method. And knowing this is fun because it's quite easy to do, even for you to, if you're offered with a velocity distribution, by doing a little bit math, you can track how does this is still the mass, yes, then you can get the mass as a function of the radius away from it, okay? And this was also from the original Vera Rubin's paper, that she's seeing some mass distribution, distance to the center, I guess this is in light. These are arrow bars, sorry. These are arrow bands. These are arrow bands.
So the picture is for many different galaxies?
No, this is for a particular one. This is for a particular one based on that measurement, yes. But these are the arrow bands. But you're seeing that the mass distribution is increasing. There has no trend of slowing down. However, the controversy is that if you look at these galaxies, even from the optical picture, the distribution of the galaxy is such that the stars are getting fainter and fainter outside. Okay? So the number density per unit volume of these stars are getting less, at least based on observation. But what's being seen is that the mass distribution is going the other way, totally contradictory to your expectation. And this is a big problem. I think that this is the most solid, or the earlier generation of the solid evidence, real evidence, that there are some mass distribution in the galactic scale that we don't know, that contribute to the matter content. Of course, at that point, people are still trying to make up some modified Newtonian gravity model, but now that part of the story has been completely ruled out. So Vera Rubin wrote in her paper that there has to be some dark matter that we cannot see that you put into the galaxy to provide additional gravitational potential in order to make the rotational curve as they are observed. Okay? So that's a lot of people quoted in 1930s, Zwicky did something, but the real scientific or very solid experimental evidence, I'd say, observational evidence came from Vera Rubin. That's my opinion. All right. This is actually a project problem that you will do. Okay, so do the same thing. Again, a Nobel Prize question by looking at our own galaxy, our sun, and looking at this velocity distribution. You should be able to figure out what is sort of assuming it's a uniform distribution, somewhat uniform distribution of the dark matter. You should be able to figure out what is actually the density of the dark matter. Oh, what did I do? Seeing the speed over here, you should be able to solve for the matter distribution around us. And this is important because it will be also important for the later calculation.
It reminds the fluctuations of the temperature of cosmic microwave background for some reason.
Correct. I will mention that later on. But this is the rotational curve was the earliest or the simplest evidence, and later on with the fluctuation of the CMB that nailed it in a more accurate form, because the CMB gives you the distribution over the entire universe. So the normal pie chart you see, how many mass concentration is in the universe came from mostly is the CMB. Okay, so let me keep going. You will work on this as part of the project. Okay, now galactic scale at our own galaxy, basically you can be convinced that in order to make up for the fact that the rotation of our own galaxy, you really have to put it into a big like fog we call galactic halo. And that halo has certain distribution, mass distribution. And in order to provide sufficient gravitational potential to trap all our own galaxy into a bound state, into a galactic bound state. Okay? Okay. So far, so good. And you should be able to derive the local dark matter density in this room, okay, within a factor of 10. Okay? Making wider approximations, you should be able to reach this. I can tell you the answer, but you should check this. That essentially every cubic centimeter in our room, we have about 1/3 of the mass of the proton that is contributed by this invisible matter. Of course, it doesn't have to be depending on the actual mass of this dark matter. Every cubic meter, you may not be able to find. You may not have one, right? If the dark matter is heavy, then every n milliliter, you may be able to find one of these particles. Okay. Now get back to a earlier question that I alluded to you. This was also almost 100-year-old picture, really made by Hubble in 1930s, also using the red shift of these stars, the distant stars away from us, and he was able to determine that the further away these stars towards us, this is 10 to the 6 parsec. 1 parsec is 3 light year, something like this. So 10 to the 6 parsec, and you see that they're moving away. And at 1 million parsec, you see the moving away speed happened to be also 500 kilometer per second, okay? So similar to the galactic rotation in the same order of magnitude. In any case, this was an important discovery that the universe is really not static, and this was really contradict a lot of people's intuition. For example, Einstein wanted to create a static universe, and he failed. He wanted to do that, but he failed. So he put in a so-called gravitational constant in his equation. He said by doing that, he could stabilize it. But it turns out, if you learn a little bit GR, you find that even putting that gravitational constant, it wouldn't make the universe stable. So it was not a stable solution in any case. So his math was not as good. But in any case, there was a history that gravitational constant retained later on. As the so-called gravitational constant we know now, it was non-zero. But this is somewhat unrelated to the fact that the Hubble observed a growing universe. Now, the current stage universe is growing. It's very easy to ask the question, what happens earlier? Yes? So you must have a childhood. You must have a babyhood. And this is the picture we know now. As it stands, we are 13.8 billion years away from the origin of the universe. So it was small and it was growing, and it is still keep growing. Okay? It turns out that for the reason that's not super obvious, that as the universe is growing, the temperature of the universe goes down. A lot of people think it's related to the thermodynamics, like expanding ideal gas. It turns out this is incorrect, because if you really use the ideal gas, you realize this is not going to keep the universe getting colder. Okay? What really happens is that as the distance scale of the universe is growing, the wavelength of the photon is also growing. And as the wavelength of the photon is growing, the frequency goes down. And that's why the universe is cold now, but it has to have a very hot early time. Okay? So this is a so-called picture that can very easily lead to a so-called Big Bang picture that we understand nowadays. But 80 years ago, such an idea is revolutionary. So the universe contains a hot history. I guess first time was Gamow who postulated the universe has a hot time. Now, why this is related? This seems to be a diversion from what I wanted to discuss, the dark matter problem. But there's some relation. Let's first go with some of the simple thermodynamics estimates. That assuming that we are in thermal equilibrium, this is the first year college thermal physics that you should understand. There's a fancy constant called Boltzmann constant, yes, that relates the thermal equilibrium, the individual particles' kinetic energy to the temperature, okay? So KBT relates to the kinetic energy of a given particle under thermal equilibrium. So at any temperature, you can compute what is the kinetic energy of these particles, so on and so forth. And this applies to all particles that are interacting. Okay? If they have no interaction, and then, well, assuming everything we know, they still have gravitational interaction. But non-interacting, you can never thermalize because they have no collision. But as long as they're interacting, even photons can also be treated as a gas. Okay? Okay, this is the wrong title. Well, this is the right title. Okay, so when the Big Bang is created, matter's coming out from this very, very hot state of the universe, and KBT gives the amount of the energy that's kind of available for you to create particle and antiparticles. Yes. Now, for example, let's take the electron as an example. In the particle physics unit, we use MeV, electron volts, blah, blah, blah. We forget about c squared, yes, as the mass of any particle. For example, what's the mass of electron? 0.5 MeV. That's easier, right? It's much easier than remember it in the unit of a kilogram, okay? About MeV is the energy scale of the electrons. So you can think of the early universe as the temperature is really, really high, okay? When KBT is so much higher than the mass of the electron, so what's going to happen? There's a lot of electron being created and positron at the same time, yes? And at the same time, when the positron and electron meet each other, they get back into photon, okay? They have electromagnetic interaction. This is called annihilation. And so it's like chemical reaction. When you have the temperature high enough, the chemical reaction goes either way. They are in thermal equilibrium, okay? So you could either have this pair production happen all the time, and you can also have the annihilation of the E plus the E minus at the same time, okay? However, when the temperature of the universe drops somewhat below a certain temperature, things can only go one way, primarily, right? Mostly. What's that temperature? Hot enough, they are in equilibrium, okay? One way or another. But at one point, it's written there?
Yeah.
If your eyes are not as good, you don't see it. The temperature goes with the mass scale of the electron, then the reaction gets stopped one way. Yes?
But do I correctly understand that for this picture to work, you assume that the kinetics of this process is so fast that you can neglect the speed of expansion? Because the universe, meanwhile, when expanding,
Yes. So the expansion.
very rapidly expanding.
Correct. Yes. Yes. So at the MeV scale, I'm ignoring the fact it is expanding. In the case of the weak interaction, the separation, we have to take into account the fact that some of this annihilation will not happen, not because of the threshold effect, but rather because the particle and antimatter cannot meet each other because they are so far away. That's a good point.
I can phrase it in a more deeper way, because
Yes.
In time-dependent circumstances, you cannot introduce temperature. You can do that only approximately, assuming that the expansion is slow enough.
Yes, yes, yes. But it helps you to at least see the picture doing this way. Okay? All right. So what happened at that point? Then at that point, photons cannot get destroyed anymore, right? There are more and more maybe producing, but as the universe gets expanding further and further, they are also harder to meet each other. So basically, at that point on, the photon cannot be reduced. Okay, it's being saved that way. So they're protected, do not disappear. Okay, and those photons, you can think of it as the primordial, the first light, the first primordial light that's being created by the Big Bang process. Okay, make sense? And all those photons could travel all the way towards us. But as the universe is expanding, like I said, all these primordial photons, the wavelength is getting shifted and shifted and shifted, all the way to our own temperature now, not 300 Kelvin. So this seems to be a very straightforward picture. But however, somewhat people really not treating it super seriously. Gamow predicted it, but only until really 1965, when a very surprising discovery was made by an antenna, okay? That Penzias and Wilson discovered there is this photon in some sense, but rather it's really the electromagnetic wave, microwave rather, that's everywhere in the universe. And it turns out that the temperature, as they discovered, was consistent with Gamow's prediction. Gamow's prediction was a 5 Kelvin temperature, but they measured something, 3.5, that was their measurement, 3.5 Kelvin in that original paper. And that was this was the direct proof that yes, the universe existed a hotter history, evolved to today, getting much colder, and that's the temperature. And this is a beautiful picture by Kobe satellite showing that it's a perfect black body of 3.7 Kelvin. Very, very accurate measurement of the universe temperature nowadays. So that's all good. Okay? Now, the reason that this photon is being measured, there is another story. That some other physics has to happen in order for these photons to be able to propagate very far. If our universe is hot to a point that it's still like a plasma, electron and protons are separated like soup. There's a lot of electricity is flowing around in the universe. Then these photons cannot travel very far. And therefore, these photons start to being free streaming at a point that the hydrogen atoms start to form. Okay? Notice that the binding energy is about 13.6 electron volts. Now, as the temperature cools to something around 3,000 Kelvin, even the tail of your Maxwell distribution, of that thermal distribution, will not decompose the hydrogen atom at this point. At this point of the history of the universe, these photons can start to travel, okay? And that was the picture. And you know exactly when they get released, and that's essentially why that seeing the distribution of all these photons across the sky also give you sort of a fossil of the universe when the hydrogen atoms start to form. And interestingly, that will also tells you structures of the matter distribution at that point. So let me see if I can give you this picture. Yes. So it was a perfect black body spectrum unless you really look very carefully. People found in early 2000 that the fluctuation point to point across the sky, instead of being a mean value being 2.7 Kelvin, you also see some fluctuations point to point. And this fluctuation is of the order 10 to the minus 5 in temperature. Okay? 1 part out of 10,000. And the reason of that is due to the fact that the universe is not uniform, but rather clumsy, that there are some mass that can attract more mass, and once you have more mass, you have more visible matter, for example, hydrogen, which makes this more concentrated region hotter, and so on, so to speak. So the hotter and lower and colder temperature corresponds to the matter distribution, whether it's a little denser or it's a little diluted. And by this map, if you measure it very carefully, then you have to really combine it with the cosmological models. Then you can nail the matter distribution when the universe is the hydrogen atom's age. Okay? And this actually turns out to be the most accurate measurement of the so-called matter content of the universe throughout, right? This not galactic scale, but the universe scale. This is something I couldn't show with PDF, but you probably saw this online. There's many of such videos on YouTube that if you start with something super uniform, but containing some local distribution of masses, and this local distribution of masses can become the center of gravity to attract more matter, and then the structures start to grow. And as we observe the universe nowadays, there's all kinds of structure. It's very clumsy. They could be started from 10 to the minus 5 level of the non-uniformity and track it all the way until nowadays. Okay? So people have been doing the simulated the universe compared with today, and it was a beautiful agreement. You couldn't even see which picture is real, which picture is made up. Okay. Did I go the wrong way? Okay, so I'm forgetting a lot of the other evidences, but combining all these galactic level of the evidence and the evolution history of the universe, as well as other evidences, this is firmly established nowadays that we have a universe with proton and electron mostly contributing to about 5% of the total mass content, mass energy content of the universe. And a bigger pie, a piece of pie, is the dark matter, unknown matter, which is about a factor of 5 more. And then the universe is accelerating in expansion. And that behavior was characterized by a term which is called dark energy or cosmological constant. And that constant is so strange, it's so small compared to sort of, the electromagnetic wave, electromagnetic field, or the Higgs field. It's so much smaller than that, and it's super, super unnatural to have it, but it's there, okay? So we have a lot of understanding with the normal matter, very, very deep understanding of normal matter. We have a bit of the understanding with the dark matter by measuring how the galaxy rotates. But for dark energy, that's even more untrackable problem, at least in terms of physics. Physics-wise, we have very little models even to describe or reliable or testable models to describe the dark energy. So both known matter, it turns out, both known matter and the unknown matter, from the Big Bang picture that I just told you, everything was created 30.8 billion years ago. Okay? You think we are young, right? You guys are 20-year-old, but your proton inside you is created 13.8 billion years ago. Okay? So those are fossils. And dark matter is the same kind of fossils. We don't even know whether it is elementary particle or not. But all the known matter we know has sort of fundamental structure. Therefore, we hope that dark matter maybe also have some fundamental unit. Yes. Yes.
It seems that dark matter doesn't present in solar system in big amount, at least, because otherwise it would change the orbits of the planets.
Yes.
Doesn't it mean that it cannot be elementary particle? It should be something heavy.
So if you
It should be homogeneously distributed
Right.
On the universe scale.
So
Meanwhile, in solar system, it's almost.
this is a typical engineer's type of question. They keep asking me whether this is bogus because you cannot really observe it gravitationally in the solar system. But you work out this little exercise computing how much mass is contained. You know, I tell you 1 cubic centimeter is that much, and you compute in the solar orbit how much is that mass. It turns out to be totally negligible to drive the motion of the planets. So it's just the integral mass. It's too small.
If you integrate this density of a solar system, you get small amount. Meanwhile, if you integrate it over the galaxy, you get something substantial.
That's
which changes.
yes. Okay. So, that tells us nothing about the actual. For example, nowadays still there's a small window of the small black hole could still be the dark matter. But they're so small that you cannot really see them, okay? So what happens is that, let's take a lucky guess.
Then there is a problem. If the black hole is small, then it probably radiates Hawking.
That's right. So if it's light, Hawking radiation makes them radiate too fast. So there's a tiny window that just happened to be making it stable, but still not contradicting with all the other optical measurements. Micro-lensing measurements. So there's still a tiny window, but you know why it has to living in that window, we don't know. Okay, so that's still possible. I was just about to say that the dark matter could be multi-component as well. Okay, just like our standard mass. Okay, you probably heard the slogan that the mass of everybody was generated by Higgs. Higgs is the master of all masses, which is incorrect, right? So Higgs only generates the fundamental fermion's mass, but the majority of the mass of the known matter are protons, not electrons. Forget about muons, you know, those are unstable. But proton mass is not caused by the quark's mass, okay? They are caused by the interaction, okay? In fact, you can think of, you know, if there's no strong interaction, if you put 3 up, down, and some quarks together and push them as a ball, this electromagnetic interaction could also generate a mass, okay? So interaction could also be part of the reason of producing mass. And therefore, just as, you know, the majority of the known matter, the mass was produced by the interaction. However, nobody forget, there's also electron, there's also muon, and so on, so to speak. Therefore, the contribution to the mass of a dark matter could be also multiple particle. But hopefully there will be one dominating one that we can find, right? There could be X% of the rest that we will spend the next century trying to discover. But hopefully this is a question that we can ask, what is the majority content of the dark matter? I would say that 20 years ago even, people still think that there is a vanilla model that to think about. For example, let's say the dark matter mass is really at the mass around the Higgs mass, because this is where the electroweak symmetry start to break, and we don't quite understand what's going on there, so it's likely that some particle is responsible for it, so on, so to speak. So I don't know. This is a prejudice. I don't know whether it's true or not. Nobody knows. But it's being challenged, I'd say, 20 years later as we stand now. Anyway, if we have such a particle elementary, you could still imagine that, assuming that they have some known interaction with the visible matter, okay? And they could still be a very hot equilibrium in the early universe, yes? Because they are interacting as the temperature is going super high, okay? So the annihilation process for these particles and the creation of these particles could also be in thermal equilibrium. So XX, YY represents the dark matter and the known matter. Okay, let's just for this discussion. Why it's not going down? Okay. For the same picture I was just talking about earlier, electron, positron creating a pair of photon. Let's imagine that dark matter is heavy, and they can be annihilated into some lighter particles, E plus E minus, quark pairs, blah, blah, blah. Okay? And then in the early universe, the other way around is also happening. They are in equilibrium until the universe cools down to a point where the temperature is getting lower than the mass of the dark matter particle. Then the number density of the dark matter can only be reducing from that point on, okay? Because when they meet each other, they kill each other. But the known matter particle, when they go together, they are not hot enough to create dark matter, okay? However, now we also have to take into account the fact that the universe is also expanding. And as the universe is expanding, the particle and antiparticle of the dark matter is further and further apart, and they are harder and harder to meet each other, okay? And therefore, technically speaking, at that point on, the dark matter start to sort of decouple, meaning they live there forever, okay? They're decoupled from the standard universe soup. And the density that we observe now, today, will be directly related to how strong the dark matter particle are interacting with themselves, creating standard model particles. Okay? If they are interact too strongly, for example, they are too easy to annihilate, and then you imagine that the number density that we observe today should be lower, right? Because they are more likely to annihilate, go away, and vice versa. If they are weakly interacting, on the other hand, okay, because they are not so often to annihilate, then the observed number density of these dark matter, or mass density rather, will get higher. So this is a so-called freeze-out picture. It may not be the only picture to create dark matter, but this is a sort of a well-accepted, well-motivated model that in regard of the initial density, the equilibrium density or the observed density nowadays, the radical density, will become a constant tying to how strongly or how weakly these dark matter annihilates with themselves, okay? And then conversely, based on the observed density, you could also ask, what does it require to have the annihilation interaction when the decouple happens? And it turns out that if you do this computation, the so-called interaction strength happened to be very close to the weak interaction scale. Okay, weak interaction as we know. Okay, exchanging of the W, exchanging of the Z particle. Okay, that kind of strength. So it was very interesting. Whether it's a coincidental, we don't know, but it's an interesting fact. Okay. So now let me talk about only one single class of model, which I will focus on, which is the so-called weak interaction massive particle. That was sort of people start paying attention to it starting from late 70s when the standard model has been completed, and it becoming a real term, I think in 1980 or so. And people think that new physics particle, trying to solve the issue with the electron weak symmetry breaking, so on and so forth, produce or predicted some particle which are quote-unquote weakly interacting, okay? They may not be exchanging a Z and W particle with the known sector, but they are trying to solve issues with electroweak symmetry breaking. So their interaction scale for these particles with the known quarks and electrons of the order weak interaction. So at that point, the so-called WIMP, weak interaction particle, weak really refers to the weak interaction, okay? And nowadays, if you ask people 50 years later, what does this weak mean? People say, oh, we will say, okay, weak means feeble, weakly. It becomes an adjective. You know, it could be something that's even weaker than the weak interaction. We don't know what type of interaction it is. In any case, I mentioned that this particle physics model predicting a weak interaction very luckily can also reproduce the observed matter density, the radical density of the dark matter. And for that, the one way is the cosmological evidence, and one way is the hint or the prejudice from particle physics that there has to be something trying to solve the electroweak symmetry breaking problem. And so that's why the so-called weakly interacting massive particle was such a nice coincidental, but people trust that this is the right path. But there are many, many other models now. Hopefully, maybe at the end of this lecture, I will talk about, end of tomorrow, I will talk a little bit about axions. But there are also stereo-neutrinos, a special type of neutrino which is heavy, blah, 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 and even primordial black holes. There are too many, but none of them really have a convincing signal so far. That's the irony. Okay, so how do we actually go ahead to detect these type of particles? One thing I mentioned to you earlier, the galactic rotation for sort of a star around sort of a medium-sized galaxy, like our Milky Way, is about a few hundreds kilometers per second. Okay? If you compare that with the speed of light, that's about 1,000th of the speed of light, conveniently. So early in 1985, Edward Witten and his collaborator made a proposal that because we know the speed of the star relative to its galactic center, and assuming that the dark matter is an ideal gas-like halo surrounding the galaxy, okay? They have their own orbital motion, but because dark matter themselves are not so strongly interacting, every dark matter is its own particle, okay? They don't like hydrogen forming bound state. They are their own doing orbits, but everybody is independent, okay? They are falling in their own gravitational trap, but otherwise they are just doing ideal gas type of motion. Unlike the rest of the galactic disk, which are mostly rotating around one direction. If you take that picture, then essentially the solar system is moving with a fixed velocity relative on average to the dark matter gas that you are trying to hit on. And because of that, you all of a sudden have a relative dark matter beam shooting towards all the atoms around us. Yes? And that speed is 1,000th of the speed of light, and the mass is whatever you assume. And then you have a beam experiment. You have a beam experiment to detect what happens after that type of collision. Okay? So that was this proposal. It was very simple, even too simple. Now, people who does such kind of measurement has been dated back also 100 years ago. Okay? For example, the discovery of neutron was precisely people at that point was using quote-unquote radiation, whatever, right? So they produce all these radioactive stuff. For example, you put alpha radiation together with some light element, and alpha can break the Coulomb barrier of this light element, producing some known radiations. Okay, alpha, we call it nowadays alpha N reaction. There's some particle or some radiation rather that had no charge, because at that point people can already put a magnetic field to know whether this particle has positive or negative charge, or electrical field rather. Both are fine. Okay, so 1930, Chadwick did such a measurement. He knew that there was some particle or some beam or some energy form that has no charge. And then he tried to measure what are the formation of fundamental particle related to this radiation. It could be photon. Photon has no charge. Okay? It could be neutrino. Neutrino has no charge. He didn't know. Okay. And he didn't even know how does this radiation interact with the rest of the world, right? But he did it anyway. Now we know that these neutrons can make magnetic interaction with atom. It could also have weak interaction. It could also have strong interaction. It turns out strong interaction is the strongest one. So, but he didn't know for sure. So it was an unknown particle with unknown interaction. But he did something really, really simple by putting this beam into a little gas detector. Okay, the gas detector, as we know, it's just whenever some particle interact with the gas, and the gas atoms gets a kick, and you measure how much that kick's kinetic energy is in terms of how many ions are being produced. So he did that measurement, and it was a Nobel Prize won 1935. It was a beautiful measurement, and he did it the way that he was able to figure out what type of this particle it is to make a direct measurement of the mass of this particle. And he made the measurement by only looking at kinetically, this particle, which carries certain energy, scatter with another particle with certain mass, what is the maximum energy that could be produced by this recalling particle? Okay? Whether this recalling particle is a nitrogen or this recalling particle is a hydrogen, you can make several measurements and make the deduction of the actual the mass of the particle. So Chadwick did this, and he was able to figure out, if you read the original paper using the hydrogen and the nitrogen, looking at the recoil, and then solve for equation that the mass of this neutron happened to be the same as the mass of the proton. And if you have an equally chargeless particle but neutrino or photon, you will get a different kinematics. These are just high school elastic scattering. Okay? If the scattering happened at 180 degree or 0 degree, you actually get either maximum or minimum energy that carried by the recalling particle, and that's it. And you then, based on that, deduce what is the mass of the unknown particle. And of course, if you go one step further, you can measure the strength of that interaction. And Chadwick didn't get that. The strong interaction was only further understood later on by Yukawa's potential, so on and so forth. But he didn't measure the cross-section, but he was able to measure the mass. Okay? But just following this train, everybody can do similar measurement by having a beam of particle going to you, and you measure what are the recoil caused by these particles. Yes? So these are simple enough. All right. So if you still remember this famous M1, M2 ball scattering that you learn in high school, and you have two equations if you're talking about one directional scattering. The energy and momentum conservation, each just one equation. You can solve for everything. It turns out I can give you something that helps you to understand. Let's say that you start defining a ratio between these two particles. Let's call it A. It turns out that the recoil energy carried by the second particle, which was at rest initially, will be related to the ratio of the two masses. Okay? So that's an easy relation. But one thing you do notice, E0 is the incoming particle. So the ratio of the mass, if it's big, or let's say if it's big, then, if the mass ratio is 1, it turns out that this term can be used the maximum. If the ratio is big or small, this is actually a huge suppression factor. Make sense? Because on the bottom, if A is really big, on the bottom is A squared. Yes? It's a suppression factor. So therefore, in order to actually get the most use of your kinetic energy, the best to have is to have balls equal mass. Just like you're playing pools, right? Playing billiard. Is it billiard balls? Yes. Okay. So anyway, this was how Chadwick got his Nobel Prize. Okay. Now here is a little question that I want you to think about. Okay. I said Chadwick did measure the kinematics. Okay, by looking at the recalling energy of either a proton and nitrogen. Okay, but if I change this interaction to any kinds, okay, whether it's a weak interaction or electromagnetic interaction or strong interaction, Chadwick in principle should see the same recalling energy. Yes? Because recalling energy carry only the info of the elastic kinematics. That's it. So what carries the information about interaction? If the kinematics tell me nothing about how they interact, well, it tells it has to have interaction, but it doesn't tell us.
Maybe the distribution, angular distribution, or
well, angular distribution maybe, but if I just take a measurement, let's say if they're all spherical distributed, for example, okay, what else carries? I can measure angular distribution.
cross-section.
Yes?
But we need to know how much particles come from the beam.
Right. So the strength of the interaction experimentally, well, you're talking about one step, which is you go from some experimental observable, you can extract the strength of the interaction. But rather in an experiment, it's not the kinematics that carry the info, mostly. It's not the kinematics that carry information of the interaction, but rather it's how fast, how frequent such a collision happens. And that's normally we call it rate, and going from that, you can convert it to a particle physics jargon, which is a cross-section. And cross-section gives you the interaction details. Okay, this is an important concept, that the rate is very, very important. I keep telling my students it's, the rate is the most important thing that you need to understand in an experiment. Okay, okay. All clear? Happy? All right. So here is a more straightforward demonstration of collision. Okay, you can think of a cross section as just a disk. Okay, and you have a man who's randomly shooting a gun, trying to hit any of these plates. Okay, so what is the condition that the bullet will hit the plate? Well, in this case, easy, right? It's whenever your bullet ends up into the area of the disk, you have one collision. Okay, so in this case, we call the cross section of such a collision just the area of this disk, 4 pi r squared. Okay, so that's in the classical sense. Same thing in particle physics sense. We almost can define something which looks like this, but it's not the real thing. It's not the real disk that we are talking about. It's not the area of the size of the particle that we are talking about. It's an abstract concept that equivalent to just how often you are hitting this disk, and you convert that into sort of a size of the disk. So cross section characterize the strength of interaction. Yep. The bigger, the stronger, and vice versa. Okay, so you will use this concept later on in your exercise, in little project. Okay, so like you said, I also need to know how often my incoming particle comes. Yes, and then you can, based on measure rate, compute the cross section. Now, essentially, how do you characterize the number of bullets or particles that is uniformly distributed with a flow? Okay, this flow can be characterized as number of particle that's traveling through any unit area per unit time. Okay, this is, by the way, called flux, if you remember. Okay, number of particle per centimeter square per second. That's the standard unit. Okay. However, if you notice, if this number is multiplied by the size of the cross section, you get a quantity, which is of the dimension of number of counts per second. That's rate. Okay. However, in an experiment setup, okay, we're not talking about just having one disk. Assuming Dima is here, inside of him contains 10 to the 100 Avogadro's numbers of these particles. Therefore, every of these little particle can be regarded as the little disk over there, right? So your incoming beam is seeing him, but not seeing him, but seeing all the 100 Avogadro number of these little disks. Make sense? So therefore, in order to compute the incoming beam scattering rate with Dima, you're not only taking one disk, but you also need to take the number of targets into the factor. Make sense? Oh, because we're talking about a flow of given particles through a given unit area. So the faster, this is not density. This is not density. Normally you can say it's a number density, which is to the centimeter cube multiplied by the length of your target. Okay, thanks. It's per Newton area that characterizes how often it goes through, Okay. Yes, this is a Dima picture, yes? So he's facing us with all these disks. Okay, so you need to also multiply by the number of targets, okay? So let me skip this because this is gonna be your project that based on the local mass density of the dark matter, you can compute the number density. Based on the number density and based on the speed of this particle traveling through us, you can compute the flux. Yes? And once you have flux, assuming you have a cross section, you can compute the rate and vice versa. If you have a rate, you can recompute what is the cross section interaction. Did I go the wrong way? Okay, so I've talked about this. Okay, I also talked about which is the most efficient way of converting incoming particles' kinetic energy into your recalling particle, yes? Think of the billiard ball collision, yes? So maximum transfer, most efficient transfer is when the mass ratio is 1 to 1, right? Imagine I have this ball moving and I punch the other ball. If it's straight line, then this ball is no longer moving. It converts all its kinetic energy to the other guy, okay? Of course, if there's a different direction, you have both balls moving. But on average, this is the most efficient way if you have two masses the same. Okay, still have a bit time to, okay, collision energy. Okay, so I've done this. By the way, there's a cosine phi dependence, but let's ignore that because mostly we can just compute the endpoint energy, meaning that assuming the collision happened in 1D. That's mostly sufficient for our discussion. Okay. Now, I will end with some thinking questions. And these will be important for your later exercise or for the later part of this lecture. Assuming the dark matter is just 100 GeV, okay? 100 GeV, the speed, let's also make it simple. It's 1,000th of the speed of light, okay? So A, estimate its kinetic energy, estimate, okay? B and C is estimating the recalling energy of this particle with two different kind of targets. One is with electron, assuming it's hitting a free electron and converting its kinetic energy to free electron, estimate the electron's energy. You cannot see dark matter after the scattering. You'll see the electron, yes? And B, how about let's choose a nucleus which is of the order 100, the atomic number 100, okay? Let's choose an atom, okay? Can you do the estimate? Okay. Let's work on the estimate. And a brave student, I hope to get your answer too. Please.
For a maybe 100 kilo electron volt.
Yes. Yes, there's actually 1/2 because this is non-relativistic. What are the other two questions? If it hits an electron, what do you get? If it hits an electron, what's the kinetic energy? Oh, you forgot about this equation, but I was alluding to you that if A is either big or small, okay, this A factor ratio between masses becomes a correction, okay? So if the mass is 1 to 1, you sort of get the maximum, right? If the mass is 1, and then over here, it's 4 divided by 4, okay? So the third question is essentially 100 keV get transferred entirely. But what about electron? What are you getting? Nobody want to say?
Which one?
You mean
A is much bigger than 1, they should use it, right?
Yes.
On the second slide,
Yes.
you were talking about nucleus, so about 100 mass, so it's equally to dark matter mass already. And we have A 0 go to 1.
Correct.
So we just need to estimate the E0, so this is the energy of dark matter.
Right.
But
So
you estimated it by answering the first question. E0 is
100 keV.
Yeah.
Yes.
Is the answer to
I'm
the
asking for the second question. What happens when it collides with the electron? Right.
Then it's divided by A. 4 times E0 divided by A,
Which is?
which is 100 GeV divided by half of MeV.
No. E0 is 100 keV, right?
No, I meant what is A.
Yes, what is A? A is 100 GeV divided by MeV. By MeV. Therefore, it's 10 to the 5, right? 100 thousandths. And that 100 thousandths is the correction factor for this energy, right? It's a fraction. Essentially, it's a fraction of the energy carried by the electron. So it's hugely suppressed. 100 keV end up only depositing 1 keV, roughly speaking, to the electrons. Okay? So this is important that 1 keV, by the way, 1 electron volts is something that's not easy to detect. It's not very easy to detect. I can show you why it's not easy to detect. So even if the dark matter interact the same cross-section with the electron and with the nucleus, just because kinematically, if you assume 100 GeV dark matter, it's kinematically more favored to interact with the nucleus, just because it's easier to get detected. With electrons, they could do it, but you cannot see it. So it's a hide and seek. Okay, it's harder to see, but the interaction could happen. Okay, there's a second effect that we'll talk about in the second half of the lecture, that also makes the nucleus much more attractive than electron. I'll discuss it later on. Okay, good. And you said you want to ask a question? Yes.
Can you show the picture with glow of dark matter around our Milky Way?
The halo picture?
Yes,
Okay.
if it's possible.
Something like this. Yes?
Okay. My question is, what about the density of the dark matter? You suppose that this density is a constant?
No, yes. So it's
And, can you set about this?
correct, yes. Thank you. So I said in the exercise that I gave out to the student to work on, you could assume mostly that assuming in a sort of, certain scale is uniform, but it cannot be uniform for sure, because this is a fact that just like as you are growing a cloud, you start from something and becomes a gravitational center. The cloud is like an electromagnetic center. When you grow it, you will have a boundary eventually. Gravitational trap is the same thing. You start from something uniform, assuming that there are some local fluctuation, but allows you to attract more and more masses. But then these mass distribution will have a boundary eventually. Yes, for sure. At the end of it, it will just have a boundary.
And how it discretes? Can you?
Oh, so you could still do the exercise by assuming assuming that you can make observation of the star, although they are much fainter, all the way out, and then based on the dynamics of all these stars, and you slice it sphere by sphere, you can still track the distribution of the mass as a function of r. But the spherical distribution was the wrong assumption to start with. So nowadays, I think people in astronomy trying to track the density or the matter distribution with a lot of help with simulation, because the Milky Way is very complex. It even has the merging history, grabbing another galaxy, and therefore somewhere there's some local angular momentum, so on and so forth. So, but you do need to use a large kind of model and the data comparison to track more accurately the distribution. But this is doable, because essentially it's what we call particle physics, the deconvolution. You go from something you can see to predict the invisible matter distribution. It's always...
You suppose that there is only gravitational...
Correct. Interaction.
That
Yes.
matter have only gravitation.
Yeah. Well, it's nowadays astronomy model are much more complex than this. They even take into account the fact there's baryon in there. Baryon themselves, meaning just no matter themselves, during the process also have a lot of interaction, so on and so forth. There's also feedback processes, so supernova blow up, so on and so forth. When people are looking at all these structures, they take into account all the known physics and try to derive the matter distribution. So but I'm describing something the simplest way of thinking about the problem. Thanks.
Okay, I guess we can have another question and move on to the next lecture.
Yes.
Thank you for your lecture. So I have two connected questions about this, about the different topic. Does the non-particle consisting dark matter type exist? And if the answer is positive, how we can detect it on Earth or in near space of us?
Let me get the question right. You want to know the non-particle type or particle type?
Yes, non-particle dark matter.
Okay. So I will mention a little bit. When people say non-particle, it doesn't really mean it doesn't have a fundamental constituent. People meant it's more like wave-like dark matter, meaning that its mass is so light that you think of its wavelength as getting bigger and bigger. So wave behavior is more than the particle. These are 100 GeV we are talking about particle-like. And so I will show at the end of the next lecture some, assuming that it's a wave, assuming that there has some known interaction with whatever field, photon field, quark field, so on and so forth. Then there's a way of detecting these Fable interaction with them.
I mean the dark matter is not particle and it is some different type of energy in the universe. Some stable objects.
Well, what you meant is probably those compact objects like black hole.
Maybe.
Yes, and those can be discussed. Well, black hole, first of all, then that means it's just a dense compact object which contains known matter. Okay, for some reason they were created, maybe by Big Bang, and they were created. These are called primordial black hole, and to detect it, various ways. I'd say people were talking about using microlensing effects, trying to see their gravitational interaction directly. I mean, that's sort of your only handle. I think the viable handle. And it could be gravitational wave. I'm not sure the gravitational wave can actually track such a small object. But the people are thinking how to really closing that window that I mentioned, which still remains for the compact object of being the dark matter. But it's very, very strongly restricted. Unlike dark matter, you still have a wide net to cast. For the compact object, I think there's only one small unknown window for them. Yeah.
Oh, yeah, thank you for the lecture.
Thank you very much. Thank you.